Good morning. We're going to finish up hopefully lesson 3.4. We're still doing a little vertical motion. The only difference is today we're gonna go to the moon. Whoa! I need a pen. We're going to go to the moon today, and gravity on the moon. Okay, acceleration due to gravity on the moon is negative 5.2 feet per second, or negative 5.2 feet per second squared. And we'll know that very soon here. So on the moon, what we're gonna do is we're gonna take a baseball and we're gonna throw a baseball straight up in the air, and we're gonna let it go up as high as it can go, and then it's gonna come back down. And the displacement or position of the baseball off the ground is going to be 65 t minus 2.6 t squared. Okay, and remember, because that's a displacement, that's in feet. That's going to be my function in feet. The velocity, okay, remember the velocity function from yesterday. Velocity is the derivative of position, is what my velocity function is. So that's going to be the derivative of my displacement function up here, which is d of t, okay? That is going to be 65 minus, well, negative 2.6 times 2, that's negative 5.2 t. And remember, that's going to be, because that's a change in distance over a change in time, velocity, that is going to be feet per, second. And then acceleration, well, remember acceleration yesterday, that was the derivative of velocity, or we need to be able to identify that as the second derivative of position is acceleration. And if I take the second derivative, or I take the derivative of velocity, what happens is I get negative 5.2. And remember, that's going to be a change in velocity over a change in time. So that's really a feet per second, which actually is going to equal feet per second squared, is how we would dictate that. Okay, so those are just my displacement, velocity, acceleration functions. So what does the object do? Well, dumb question. Well, if I'm sitting at home, sitting on the moon, and I throw the ball in the air, what we're going to do is we're looking at the action of the ball. What does it do? Well, if we actually graph it parametrically, like we will, we're going to see what happens when the ball goes straight up and it comes straight down. Okay, but what is happening to the ball? Meaning, what is the speed on the way up? So as you throw the ball and the ball is going up, is the ball speeding up or slowing down? Well, on the way up, the ball is speeding. It's not speeding down. The ball on the way up, it's slowing down. And what happens is the ball goes up, it reaches its maximum height, and when it's at its maximum height, the speed, it stops, okay? And then it goes on its way down, and then it speeds up. Okay, so this is what the ball is actually doing, and as I come across here, this is going to come down. So what is next? So what's actually happening to my position function? Well, we're going to show this, but my position, d of t, is doing what on the way up? Well, my position function is increasing. And well, that is because, and I can see that, well, I'm just going to go with it. My position, d of t, is increasing on the way up, so it's going up, and what happens is it increases to a max at d of t, and then what happens is then it decreases from there. D of t decreases, okay? It's decreasing on the way down. So on the way up, what's happening is my position function is increasing. On the way down, it's decreasing, okay? what's happening to velocity? Well, my velocity function on the way up, here, we're going to focus more on the sign of velocity. And I want to I need my eraser. I got to get this written properly here. The way for you. So on the way up, d of t is increasing. So it increases to a max, and then it decreases. Okay, so what we're doing is we're looking at what is the velocity doing. Well, remember, the velocity, in the end, that is the derivative of position. And think about the relationship with the derivative in a function. If my function is increasing, well, what does that mean? That means my derivative is positive, doesn't it? So as I'm going up, my velocity function is positive until it hits its maximum height, okay? And then it's 0. And then on the way down, what happens is my velocity function, or thinking of it as d prime of t, well, if the position is decreasing, well, that means I have negative tangents, so the sign of my velocity function is going to be decreasing. Well, what's my acceleration function doing? Well, on the way up, what is my acceleration function doing? Well, when I look at my acceleration function is constant. So my acceleration is always negative 5.2 here. So, in other words, it's negative. On the way down, it's negative 5.2, or it's negative. Now remember, acceleration. That's acceleration due to gravity. Gravity is not affected by the ball, okay? It's always being acted on by gravity. So when I'm at the max height, well, what's my acceleration at the max height? Well, again, because it's constant, it's negative 5.2 feet per second squared. Okay, so that really didn't change anything. So we're looking at, what we're doing is we're going to be comparing speed and displacement, velocity, acceleration as we're coming through here. Okay, so as I'm looking here, what's happening to the velocity of the object during the flight? Well, v of t, my velocity function, v of t, well, I know what that is. It's 65 minus 5.2 t. It's linear, okay? So what's happening to my function? Well, I can check this out, okay? I can graph this. I know my y-intercept is going to be somewhere here at 65. Smartboard's working really well. It's up here at 65. And my slope is negative, so it's going down forever, and it's going down at a constant. And what I do know is if I'm looking here, okay, and I'm correlating what's going on here, when my velocity is 0, whoa, connections. Here, I'm at my max height. And I can also see, okay, before that, this is like going up, and then this is going down, and I can read this off of here. So I know as I'm going up, and then right here, v of t equals 0. It's bad, which means it's a max height. And then, missed my n there, it's going down. So what I'm going to be doing is we're going to be comparing this stuff. Now, notice my velocity is always decreasing, okay? However, just think about this. What my velocity is doing is I'm going from 65 feet in the beginning, and then I'm going to 0 feet, and then I'm going to something negative feet per second. I should have my units on there. So it's always decreasing. My velocity is always decreasing. Okay, it's just going down, all right? So we're going to move on here. Now here's where we're going to actually graph this. Now I'm going to graph this parametrically, and I'm not going to graph it in a parametric quite yet. We're going to know how long is the ball in the air. Well, here what I got is I got a quadratic equation. And how long is the ball in the air? Well, the ball is in the air as long as it's not on the ground. So I'm trying to find when is d of t equals 0. 55t minus 2.6t squared. And when I look at this, oh, it's quadratic. Now, on my tests, unless a calculator is available, you wouldn't have problems like this. In the AP test, you wouldn't have a problem like this, although you should be able to solve this because we can see at least I can factor a t out. Then I'd have 65 minus 2.6t. And I know t equals 0 is the beginning when the ball is thrown. And I know 65 minus 2.6t, that equals 0. It's just setting these equal to 0 when t equals 12.5 seconds. No, 25. Okay, t equals 25. Now, you can get that with your calculator or solver. Okay, you can use the solver to get it, and if you did, more power to you. We will use solver. Actually, I'm going to review solver really quick for those of you at home that are not doing things the way you're supposed to. So, go to a calculator page. We are going to add, no, I'm not adding anything. Hold on. And on my calculator page, I don't want to be. Come on. This is really annoying. So I need to add a calculator page, and I need to add a calculator. And on here, to use solver, I'm going to go Menu, Algebra, Solve. And inside here, I'm going to say, hey, when is it equal to 0? And when I'm using solver, I can type in my function 65t minus 2.6t squared. And it's kind of nice. And I can say, now I have to tell the calculator with a comma, please solve for t. Okay? And it gives it to me 0 or 25. So I do have my zeros. Well, because it's quadratic, this shouldn't really be too much of a big surprise. We can kind of look at this. So if it was at 0 when it started, and it was on the ground 25 seconds later, obviously it was in the air for 25 seconds. Okay? And we can look at all this stuff and we can make a graph of this because I know right here is where it starts at 0. Right here it's back on the ground at 25. And thank goodness for Algebra 2 because I know somewhere in there this is going to go like this. And I know right here in the middle is where my maximum happens, right? So that's basically at 12.5 seconds. So I can find my maximum in there if I really needed to go in there and find that. There's all kinds of stuff, and my parabola opens down because A is negative, blah, blah, blah. So how long was it in the air? It was in the air for 25 seconds. Now, what I'm going to do, you do not have to do this. You will not have to do this on the AP test. But what I really want you to know is it is not the path of the ball. The actual path of the ball would have to be graphed as a parametric. And as a parametric, you guys did do these last year, I was told. I asked Mr. Linsmeyer. And when you're graphing in parametric mode, basically you're just creating a whole bunch of ordered pairs, okay? Both of these ordered pairs will be functions of a third variable. And I know you did them because the first parametric that you did was working with the unit circle. Think of all those little ordered pairs on the outside of the unit circle. They were sine and cosine. They were both functions of t on my t-axis. And what I did was I was plugging t into those functions to get these out. And we had all those little pi guys around the outside as the ordered pairs that we found for those t values. But as we're coming along, okay, we're doing some ordered pairs. We're really looking at an x of t and a y of t. Now, don't worry about this. I just want to graph this so you can see how you're going to graph, or the actual path of the ball is different from that parabola on top. Well, when we're graphing in parametric mode, because this particular ball had no horizontal force put on it, it was just basic. It was thrown straight up or down. I'm just going to throw my first parametric there as a 1. Now, this is just so I can see it up or down. I can make that anything I want. And the height of the ball is going to be my y value, which is going to be 65t minus 2.6t, okay? And all this is going to do is this is going to show you the actual path of the ball that the ball traveled. It's kind of neat. I don't know. I like looking at it. So I'm going to come back here and to my graph. Now in order, this is function mode that I'm in. So in order to graph as a parametric, I have to change my graph entry and I have to come here to number 4, a parametric. This window should come up and notice it's kind of set in for trig functions already because my t variable is going from 0 to 2.8 or 6.28. Looks like 2 pi to me, but I'm going to enter my two parameters. I got a 1 and the other one is 65. Now notice all these parametrics are in terms of t, you know, like time, minus 2.6 t squared, 2.6, not 2.2, 2.6 t squared. And what I want to do is I want to change my time to match the time the ball was in the air. It went from 0 to 25 seconds. And I'm going to make each step into a half of a second. Okay? So what I can do is I'm looking for, when I graph this, so now I got to change my windows like it says over there on the side. So I'm going to go menu, just so I can see everything on here. Graph entry, no, window zoom, settings. We're going to go from -1 to 2 with my X scale at 1. And because this ball is going to go pretty high, I'm going to go to like -100. And I'm going to go up, and I'm only going to -100 because I'm going high, and I like to see my x-axis. And I'm going to put my step at about 50, and I'm going to say OK, and I'm going to move this. Now, when I trace this graph, okay, when I trace this, what's going to happen is I'm going to see the actual path of the ball. And the actual path of the ball is going to move. Okay, menu, and I'm going to trace it, and I'm going to trace the graph. Okay, and I'm going to be back. Okay, so as I'm tracing this, what this is going to do is kind of cool. I'm just holding my arrow down where you're doing the same thing, and it's showing the path of the ball right up there. Okay, notice if you look down there, right there, it's at its maximum height, and my maximum height is, I need this thing to write, so hold on. Get this guy. Oh, it's not going to work for me because it's not working. Okay, so I can't draw on there, but I can see my maximum height right here because I should be screen sharing. And I know I'm at my maximum height because I'm at 12.5 seconds. Now this is doing a whole bunch of ordered pairs. This is not giving the position of the ball. This is just moving things up and down. If I come all the way down here, come on, baby. Menu, trace my graph. I'm going to bring them all the way down. Bring them all the way down to t equals 0. So that's where the ball starts. Now, I can see, obviously, I mean, it only makes sense that my position is increasing because I can see my ball is going up. And I can see how it's going up right here. It's at 31.85, and then it's 64. So the ball is going higher and higher and higher. So the ball is increasing in height all the way until it gets right up here to 12.5, then it stops for a second, and then it decreases. Now, it's decreasing in height because it's going back down, all right? So also, look, now when I said my velocity is increasing, well, think about this. As I'm going up, my change in height, okay? My change in height is going up and going down, so I'm just coming up, and I'm just kind of liking the looks of this. It's kind of fun to watch. Woo, there's the ball going up, stops, and it comes back down, and it hits the moon. Okay, so that's actually modeling the path of the ball if I threw it. If I was modeling it as a function, it would look totally different. It's going to look like the parabola that we drew before. So this is what it looks like to actually graph the path of the ball. It goes straight up, comes straight back down. So I could also go through here and compare, which I'm not going to do because this one won't trace it. And I'm going to come right here to my next page, and I'm going to go skip it on. Okay, how high does the ball go? Okay, so I was looking at my increasing, decreasing. That was the path of the ball, showing that everything's going up, going down. If you're taking all those things, I can see that my velocity is increasing because my change is going up, and we're going to see all that in a minute. So, how high does the ball go? They want us to use some calculus to find that. Ooh, what does using calculus technically mean? Well, to me, using calculus means no calculator within reason. Now, we're going to use our calculator just for number crunches. Now, the reason why we're saying use calculus here and not a calculator, it doesn't take too much knowledge to come in here, add a new page, add a new graph as a function 65x minus 2.6x squared. Graph that and say, well, oh yeah, I remembered. My maximum height went up to like 240 something, I think. So I'm going to come here to my window, and I'm going to go my window settings. I'm going to go from like -10 to like maybe 30. And I'm going to make that about, I don't know, 5. Doesn't really matter. And here, my minimum, I'm going to go -100. And I'm going to put this at 450 because that ball went way the heck up there. And, you know, if I look, now this is the height of the ball as a function of time, height. Oh, I can see my maximum right here. It doesn't take a genius to type this into the calculator and say, analyze graph. Please find the maximum. Where is it? Oh, there it is. It's at 12.5 seconds, and the max height is at 406.25. That's not using calculus. That's using technology, which you will do that sometimes. But if I use calculus, how do I find that? Well, think about this. When I'm at my max height, okay, when I'm using calculus, I want to find my flats. I want to find a maximum or a minimum. So if I found my max height, what do I connect at my max height? Ooh, my velocity of the ball is going to be 0. It's going to be stopped. So what I'm going to do is I'm going to come, whoa, went too far. I'm going to come back here, and we're going to use some calculus because my position function, d of t, 65t minus 2.6t squared, what we're going to do is we are going to find d prime of t because that's v of t, right? If I take the derivative of position, I will get velocity, and that is going to be 65 minus 5.2t. Well, if I know my velocity equals 0, that's going to give me the time at which I reach my maximum. Well, if I did this, I got 5.2t equals 65, okay? These numbers, if I didn't want you to use a calculator to crunch the numbers, they would be mental mathers. I'm not going to ask you to do this. But 65 divided by 5.2, guess what it is? It's 12.5 seconds. If you don't believe me, check it in your calculator. I'm not going to have you longhand divide that. But that's the time. That is when the max occurs. They want me to know how high does it go. So now that I know how high it goes, now I need to plug the time at which I know it reaches it into my displacement function. So I'm trying to find d of 12.5 because I want to know its position. So that's going to be at 65 times 12.5 minus 2.6 times 12.5 squared. And again, no, I totally do not expect you to do that without a calculator. That would be unrealistic of me. So you would type that into your calculator if you had one, and you'd say 406.25 0.25 feet is the maximum height. That's the maximum height that it got there, okay? So, bottom line, what I'm doing is I see my 0 here, okay? And I see another 0 here. This was 25. This was 0. Because we knew this is parabolic. Huh. I went a little too nutty there. Get that? I know this is parabolic. And say there. Good old Algebra 2 says there's my maximum. That's terrible. And oh boy. And you know, I could go through and find my intercepts, find the middle, but notice the middle here at the 12.5, that's my flat, so I don't have to get this graph. That's why I found my velocity function. I set it equal to 0, and I said, hey, when are you 0? Because that's when you're flat on this maximum, okay? Now, number 4 is saying, what is the velocity when the ball is 390 feet high? Well, let's look at this. How am I going to find that? Well, in order to find my velocity of when the ball is 390 feet high, I need to find the time the ball is 390 feet high first, don't I? So don't I have to come here and take my displacement function and say, 65 minus 5.2, 65, don't I just have to come here? Where's my stupid position? 65t minus 2.6t squared. Am I just not just saying, when are you 390 feet? Okay, 65t minus 2.6t squared. Again, AP test is not going to ask you to solve something like that, nor am I. If you set this thing equal to 0, it's going to be factorable. So that means we are going to go to our solver here quick. And I'm going to come in here. And I'm going to copy this little guy because I already got him in there. Only thing different is I'm going to squirrel over here and I'm going to say 390 feet. So what time is it 390 feet? Look at those nice answers, okay? Gives me 10 or 15, so it's actually at that height twice. Shocking, isn't it? Because here it's in t equals 10 and when t equals 15, I think I said, right? And t equals 15. Shouldn't be too shocking, okay, because I knew up here that was 406 feet, 406.25, and that was 12 point, oh boy, I can't write a damn thing. So this is 12.5, comma, 406.25. So if I was under that, my 390 is somewhere across here. All right? So I'm looking for this intersection and this intersection, which I could. Now there's a reason why I'm drawing those on that graph at the same time. Now the other thing, now I know the time at which I reached 390 feet. They want to know what the heck is the velocity though. Okay, so that's going to be taking my v of t function, which happened to be what? 65 minus 5.2t. So in order to find my velocity at 10 seconds, I need to find v of 10. Well, isn't that 65 minus basically 52, right? I hope that's what it is. So that should give me what? 13 feet per second. This 5.2 times 10 is 52. And I also need to take v of 15. Now, if you're really thinking about this, you're like, oh crap, minus 5.2 times 15. I don't know what that is. I need my calculator for that. Think about the wonderfulness of a parabola. Okay? When I'm here at 10 seconds, when I'm at 10, 390, okay, the velocity is my tangent line there. That's 13 feet per second. Ooh, that's at the same height. There is symmetry here. What's that one? That's the same tangent. It's just negative 13 feet per second because of its symmetry. Okay, and that's unique to your parabola. Okay, and where do we go from here? I think we go to the last page from here to try to tie this together. And I'm moving everything. So, look at this problem in function mode. Did that already. My problem in function mode is going to come from here. It's going to be at 0. It's going to be back down here at 25. I know here in the middle at 12.5, I'm getting my maximum of 12.5 comma 4, oh boy, 12.5, I needed a comma, not a parenthesis, comma 406.25, and I knew it went like that. Now that's in function mode. This is time, and this is height off moon. Okay, it's height off the moon. What we want to be able to do, okay, my goal here, might say, hi, transitioning to this, but the goal is to look at this problem in function mode and say, when is the ball speeding up and when is the ball slowing down? Okay, my goal is you need to be able to tell me if it's speeding up or slowing down from, number one, the displacement curve. You need to be able to look at the velocity curve, tell me when it's speeding up, when it's slowing down. And you also need to be able to look at the speed curve and say when it's speeding up and when it's slowing down, okay? So we need to be able to interpret all of these at the same time. Now, I do know when the ball is speeding up because I got that from the very first page here. And my very first page is all the way back here at this yellow one, okay? I knew the ball is speeding up from time 0, and then it reached its max height at 12.5, and then it was on the ground at 25, okay? So I knew when it's speeding up, when it's slowing down, okay? So I'm going to come back to my page here, if I can find it. So I know the ball is speeding up on the interval from 12.5 to 25. And I know the ball is slowing down from 0 to 12.5. The question is, how do I tell that from my position graph? This is my d of t function. This is my position function. How can I tell that from the function? When is it slowing down? Actually, I'm going to go slowing down. No, I'm going to keep them in the same order. Sorry. Doesn't really matter. When is it speeding up? And when is it slowing down? That's the question based off the displacement curve, okay? Now, what I'm going to do here is I'm just got nothing to do but to give it to you. Speeding up, slowing down, that's talking about change in displacement over change in time, right? Okay, so I'm kind of looking at things, and that's really alluding me to looking at a velocity, and I know my velocity is the derivative of position. So my velocity, when I'm looking at all these curves, I can see right here on my position curve, what am I doing? Well, that's from 0 to 12.5. I'm slowing down there. How would I look at that and say I'm slowing down? It's the steepness of the curve. I'm going from steep to less steep. My tangent lines are slowing down. The slope of my tangent lines are getting flatter as I'm coming in, okay? So I look at this and I say, well, I'm slowing down when tangent lines are getting less steep. getting less steep, okay? My slope is decreasing. The slope of my position curve is decreasing. When I'm saying the slope of those green lines are getting less and less steep, meaning the slope is decreasing, so therefore I'm slowing down. When I'm speeding up, look on the other side, what's happening to my tangents? My tangents are getting steeper and steeper and steeper. Therefore, I'm speeding up. Okay, so it's the steepness of the curve. I'm going to say tangent lines getting steeper. I'm going to say there, tangent lines getting steeper. Meaning slope is increasing. Slope of the tangent lines. The slope of those green lines from that to the right are increasing. They're getting steeper. The steeper the tangent line, the steeper the slope. Therefore, it is increasing. How can you tell this from the velocity curve? Well, I guess in order to get the velocity curve, I need to kind of plot the velocity curve. I'm going to make it that guy. Now I know here, and I'm just going to go, it kind of looked a little something like that. And I'm going to go on a whim. I'm going to call that my 65, my velocity at time 0. Okay? So can you tell that from the velocity curve? So now I'm just looking at that little purple one. Here it's on the ground. And yeah, I can. Slowing down, speeding up. Well, looking at that, what am I looking at? I'm going to say speeding up. Slowing down. So, when the heck is my function speeding up? When am I slowing down? Well, if I read this graph like I'm supposed to read this graph from left to right, okay, what do I see? What I see is my velocity is coming right here. Now I know right here, at that time, I'm stopped. Right? Right there, it stopped. My maximum height, it stopped. Okay, what's happening to the left of here? Well, what is happening? My velocity is going what? What's happening to my velocity? My velocity in value is getting smaller, but I can't say it's because my velocity function's decreasing, okay? Because I'm decreasing over here too, but I'm not constantly slowing down because I can see I slowed down and then I sped up down to the bottom of my position curve. So what I'm looking at here is I am slowing down from left to right when my velocity function approaches 0, okay? So when my function, I'm slowing down when velocity graph approaches 0. When my velocity is approaching 0, left to right, getting close, I'm approaching 0, so I'm stopped. And then as I move away from the x-axis, as I move away from that 0, I speed up. And now, remember, when I'm saying 0 here, I'm envisioning the x-axis because that's when my function is 0. It's right there at the x-axis, okay? Well, how can I tell this from the speed? Well, remember, speed is the absolute value of velocity. So all that does, the only thing that happens to my speed curve is my speed curve is going to come over here. So this is going to stay the same. That's going to stay positive. But now this side, what was negative is now positive. Okay? So I can tell this from the speed curve really easy. as my speed decreases, okay, it's going down, and here it's increasing, meaning it's speeding up. So that part's pretty easy. Slow down, speed up. So I'm going to say speed up, and we're going to say that's when speed increases, and slow down, that's when speed decreases. Okay, because speed's always positive, so I can look at it. If I'm decreasing, I'm slowing down. If I'm increasing, I'm speeding up. It's as simple as that off of my speed curve. Okay, now the kicker is, what I want to do is I want to look here, and you will have problems like this in the AP test, I promise you. Okay, and what we're going to do is we're going to look at here. There's faster, easier ways to do this, kind of. I'm slowing down from 0 to 12.5. I'm speeding up from 12.5 to 5. What do I know about my acceleration? Well, my acceleration was constant. It's negative 5.2, meaning acceleration was negative. Still negative 5.2 on this, meaning it's negative. Okay. What was my velocity on 0 to 1 point or 12.5? What was my velocity up here? So my velocity function was positive, wasn't it? So because my velocity function was positive, I can see here, okay? And from 12.5 to 25, my velocity function now was negative, wasn't it? Because I can see that right here. Here's my velocity, purple. Now my velocity is negative. So when I'm comparing, what we really want to do is we want to compare, velocity and acceleration. When velocity and acceleration, when they are opposite signs, okay, they are working opposite each other. They work against each other. Therefore, it slows down. Okay, now think about it. When we took the ball and we threw it up, it was increasing, wasn't it? Okay, my velocity was positive as it was going up. It was slowing down, but it was positive because all those tangent lines, when I was looking on my position, those were all positive up to there. So when I'm throwing it up, gravity is working against it, pulling it down. Slowing it down is my theory on it. When the velocity is negative, well, now it's on its way down. Now my velocity is going down. Acceleration's pulling down. They're working together here. Therefore, speeding up. Okay? They will ask you, here's a particle moving along the x-axis. We'll do horizontal motion later, tomorrow maybe, but it's going to say, here it is. Tell me when is the object speeding up? When's it slowing down? When's it moving up? When's it moving down? When's acceleration positive? It's going to ask you a whole bunch of questions, but most of them will be on horizontal movement for that, because vertical is really kind of boring. But here's where we want to see when acceleration, or when velocity and acceleration are working, when they are opposite signs, when they work against each other, my object is slowing down. But when they're the same signs, they're working together, therefore they're speeding up. Okay, that's the main thing we got out of here. Good luck. Have a good rest of your day.